Any questions from the last class? Any questions about logistics or anything? The assignment 1 will be up very, very soon. But any other questions?
Did you record the last class?
I did.
Sir, can we get the record?
Yes. You have to find out how.
It's not
That is left as an exercise. It's not very hard. I will put the link, but it's not very hard to find out where it is.
But last 2 classes are recorded.
No, only last class is recorded. Also, I don't know how useful they are because earlier when I first started recording, I used to do a lot of work on. I used to use iPad to record that also, but that technology never works out properly. So I do a lot of board work now. So I don't know how useful that is. But yeah, it's available online. Okay. So we had started this problem, if you remember, and that's where we had left. So we'll finish that and think about why is the lecture called categorical data? What is categorical data? So this is a study about breast cancer, whether having babies at a later stage, is it associated with having higher risk for developing breast cancer? So you're given this kind of data where it's broadly this is where the categorical part comes in. Right? So these are the two categories of women who give birth at who have given birth at age above or equal to 30, and one which is less than equal to 29. Right? So, and some of them will have developed are cases, and some of them are controls. So this case control setting happens a lot in biostatistics. Like cases are disease, controls are where no change happens. So among these women, there are cases and there are controls. Among the cases, among 683 women with breast cancer, which is the case women, there are 683 of 3,220 people or 20 women who have given birth age less than equal to 29 years, right? And finally, for the case women, sorry, it's better to just write those numbers down. So help me write these numbers down. What is the number here?
683.
Yeah, 683. And here?
149.
Okay, and of course these total up to something, so we can always derive what that total is. And how much is it here?
1024.
Is that correct? And this number is what? 21% and 14.6%. So this is 21.2%. This is 14.6%. The goal or the question that we're asking is how can we assess whether this difference is significant or simply due to chance? Among the women who give birth to at the age of above or 30, is there, in other words, right, like what is the question that you're asking? Is there, in other words, higher probability of developing a breast cancer or having a higher risk of breast cancer if they give birth at a later stage? So how would we assess this? How would we think about whatever we have discussed in the class? How would you try to see whether this makes sense? Any ideas, thoughts? So again, the problem with this class is it's a recipe class, right? Like in some sense, you have to think about the recipes. But before we develop that recipe, what is that intuition that we're going to use? That's what we're going to try to develop first. So in a scenario like this, if you were to test this, right, like why is this kind of a design different from what we have seen so far? Why is what, if at all, is different from the design, right? That's the first thing that you think about. What is the design of this experiment? So if you remember in the last few classes when we did the example, we always talked about what is the design of the experiment. Right? The first thing that you have to think about is it a random sample? Is there independence? Is this paired setting? Is this unpaired setting? All those kind of questions will help you understand what is the design. Is it paired? It's not paired for sure, right? There's no way it can be paired. Are these cases independent? So it's definitely unpaired. And are these rows independent? They have to be independent. Because that's what it says in some ways, right? Like that when you actually controls were chosen from women of comparable age who were in the hospital at the same time as the cases, but who did not have breast cancer, right? So these women whom you profiled, they happened to be in the hospital, but they were not having breast cancer, and that's why they are controls. But there is no relationship between these two, and that's why these are independent choices. So anytime, this is the kind of exercise that will be useful, of course for this course, but also in general to think about what is the design of the experiment. Right? Like, it's a very simple exercise, but a lot of us, including people like me, don't do it, which is just to think about what is the design of the experiment, right? So pay a lot of attention. Okay, so now, right, how would you test this? In all the previous classes that we have done, right, 4 classes so far, there was something that we were doing. What is that common theme that is not present here in some sense? A null hypothesis. So what is the null hypothesis here? What is the null hypothesis? This does have a null hypothesis. What is the null hypothesis?
The difference is insignificant. The difference is insignificant.
The difference is significant, or is not significant, right? So the difference that we see, so I'll not write the same thing, but I'll just call it P cases is equal to P control, where P is the probability of developing breast cancer for a certain, in the age group of above greater than equal to 30. In the case when we were trying to do t-test, z-test, or Wilcoxon, or Mann-Whitney, what did we have access to? We had some order, we had, yeah.
So I didn't P gauge is equal to P control, right? So it will be P greater than equal to 29 equal to P, P greater than equal to 30 equal to P less than equal to 20 data else.
Okay, let me answer this question first and then I'll come to it. Yeah.
I think it should be P greater than equal to 30 is equal to P less than equal to 29. So that's what we
Okay, so correct. So I chucked out a lot of details, but I'm talking only about this number. Yes. So this is with respect to this number, with greater than equal to 30. Okay. So this is in the age group greater than equal to 30. Okay. That's good. You said something.
So I was like, if we don't consider the categorical, then we are only considering one color. So we need to consider both the colors, right?
Okay. So there is some concept of binarization or categorization here, right? Which we had in the t-test or the z-test also, because your cases and controls are your groups, right? They are either part of your cases or control. This part is same. There is something here, right, which is different. That you're putting them into the same set of people into 2 different categories, and there is something associated with them. There is one more level of difference. This is the only information I gave you, right? In the case of any other setting, you would have some more information. So, for example, in the Mann-Whitney, in the Wilcoxon-Mann-Whitney test or in the Wilcoxon-Steinbrandt test, you have access to an actual observation. There's something that you're quantitatively measuring. It could be ordinal, it could be quantitative, it could be numerical, it could follow normal distribution, it could not. But you had access to individual observations. Whatever, something, whether it's ordinal, nominal, any of that. And what we were interested in is the mean distribution between these two groups different or not. The setting here is very different. You're given summary statistics. I don't have individual observations about those 3,220 people. Neither do I have for these 10,245. I don't have either nominal, ordinal, or any other sort of quantitative measurement done on those 13,000 people. All I have access to is summary statistics. That summary statistics provides me into two different categories. Either this is an age greater than or equal to 30 or less than or equal to 20. Okay, everyone with me so far? So the moment you see these kind of numbers come up, right, where there is binarization or categorization of your information, we'll try to invoke a certain kind of test and we'll come to that as to what that test is in just a minute. But hopefully this is clear that any of the tests that we have developed so far will not actually help us answer this question directly, because we don't have access to individualistic information which is required for all the tests that we have done so far. Right? We required each group to have certain observations, and then we looked at either the difference of those observations, mean difference, or we looked at the rank difference of those observations. We have none of that here. But we still want to test this hypothesis, right? Is the relative risk of developing breast cancer higher in women who give birth at the age of 30 or above, as compared to having a baby at a lesser age, for example? With this in mind, what can you think about this, right? How many ways are there, for example, to observe whatever you're observing? So permutation, for example, is your friend, right? Like, one way to think about any of these experiments that we do is to think about what is so special about this observation as compared to anything else that could have happened. Because that is a measure of your p-value, right? P-value is the probability of observing something as extreme as what we did. So in this case, what is the possibility of observing? What are some other possibilities of observing something like this? Why if at all, if this is special, why is it special? Or how will you measure it? It's a permutation combination question, right? In some sense, if you think about it.
You have a partition possible into the 4.
Okay. So what is constant here?
The sum.
The total sum in some sense, right? Like we know that when we profiled 3,220 people, which were cases, and some 10,245 people. And if that is constant, the total number, which is 13,465, those are the number of total number of people you have profiled. With this number in mind, right, we will try to think about, is there an alternate way of defining what the null should be? What is the null? The null is that there is nothing special about any of these numbers that you're observing here. They're all equally probable in this sense. So if this is equally probable, the moment you fix something here, the other thing automatically gets fixed. That's another thing that you should notice, because these two numbers will add up to the number of cases, right? Why am I focusing on this number? Because my hypothesis here is in this category. It could have been in the other category also. There is no sense to that. But the moment I fix anything with respect to greater than 30, the other one is again implied because there are only two categories. Okay, so we will talk about one step by step how to think about this design, but intuitively again, before we do the recipe business, how would you think about how should you test this? Or how will you calculate your denominator, right? Any p-value calculation requires that you observe and then you divide by the total number of possibilities. That denominator, how would we get? Intuitive.
Just multiply the
Multiply what?
3 to 1 and 1 0 to 4.
Multiply these two. No, sorry, say that again.
Yeah, these two.
These two, okay. So 3220 into 10 to the power, into 10 2045.
Into 1.
Into?
To 1.
So into 1.
3 to 2 1 into 1 0 to 4.
Okay, 3221, okay. Into?
1 0 to 4.
Okay, why is that plus 1?
Because 0 to 3 to 2 to 0 is 3 to 1 value.
Okay, interesting, right? So you're saying that the possible values that each of this number can take are 3 to 2, 1 possibilities overall, okay? And similarly here it's 10 to the power 10 to 46 because those are the number of possible numbers that can fit. Anyone else? Good. Anyone else? We'll do some recipe business because there's no way to avoid doing that. But any other thing that you can think about here? What is your expectation if you saw those numbers? What is your expectation? How different is it from null? Like how different is this observation from a null? So what would happen in the case of that null business?
Can we merge the two columns into one? Like with respect
This
to
one?
30, 30 and greater than equals 30 and lesser than equals 29. So with respect to 30, so if we make that 683 divided by 2537, that is less than equals 29. So we get a fraction that how much times 30 is with respect to 29.
Okay.
So hence eventually we are down to the same thing that we used to do in the previous tests.
Okay.
We have the cases and the control.
But only one number.
Yeah, but everything is with respect to 30 and then scale it back to 29 when we get the final result.
And how would you assign a p-value in this case? How would you assess whether it's an extreme number or not?
So it will be a only one-tailed testing because I'm testing with respect to 30 only.
Okay.
So if it rejects, we can test that we reject the hypothesis that greater than equals to 30, that hypothesis is not correct. So
And how would you, so I think, yeah, it's getting warmer, but how would you assess? Like what would be your basis of assessing? So let's come back to it in just a bit, but overall, if there is no association between getting a breast cancer and having a children at a particular age, what would you like to see? What would this number be? 683. What would this number be given this design of the experiment?
Can't we model it as a binomial?
Okay, as a binomial. Okay, what is binomial here? Which one?
The probability that the woman had the first child after 30 and contracted breast cancer.
Mm-hmm.
That will be my P1.
Mm-hmm.
My P2 will be probability that woman gave birth less than 29,
Hmm.
is the present equal to 29,
Hmm.
and contracted breast cancer.
And then got the breast. Okay, so P1, P2.
Yeah.
Okay, and this is one. So P1 prime, P2 prime.
And that will just be 1 minus P1. Right?
Say that again.
That will just be 1 minus P1.
So no, so depends on how you're defining your sum to be, right? But here you're saying that the total number of women who are above greater than 30, if they give, fine, fair enough. So this, you're summing them to, if you're conditioning on that, then that's correct. You could have also conditioned it on this.
mean, we don't need to do that. That's what I think. That's what I feel.
Okay, from here, how would you proceed?
Because if your first child came in after 30, you have some bias towards breast cancer. And if your first child was younger than 29, there was another bias. It was basically comparing these two biases.
Yeah. Okay, fair enough. So you are essentially trying to compare that if you have already developed cancer or if you have not, then depending on what, if I condition, so everyone understands what is conditioning. You condition it based on that if I'm already 30, if somebody already gave birth at the age of 30, what is the relative difference in terms of the proportions that you saw here, right? So 683 divided by whatever that total number is here would be your P1 and the remaining will be 1 minus P1, for example. That would tell me the relative risk of developing cancer in women who have already given birth at the age of 30, and you could do the same thing for 21. If I do it this way, if I do it the row wise way, it's a different interpretation. There the interpretation is what is my, among the people who have cancer, what is the relative probability of women who have given birth after the age of 30, them developing cancer, whereas in this case this is control. Is that distinction clear in terms of what happens based on what you divide your denominator as? Okay, so we are getting very, very warm in terms of how we should be testing these numbers, right? One thing that you should realize is these are simple proportions that you're going to test. So our first test will involve how can we test for difference of proportions overall in this kind of a design. So these are binomial proportions, right? The reason this is binomial is because each person has a chance of either being in category 1 or cases or controls, right? So there is a binomial factor involved in these cases. You can also see it in this fashion that given cases, this distribution as to how many number of people who end up having baby at a later stage, that follows a binomial distribution. Right? Is that part clear? Like the binomial interpretation? There's a number of people fixed and you're putting them into success or cases versus control category, right? So it's automatically that design where each person follows a Bernoulli distribution, and then we test for binomial. Okay, so whenever there is binomial, you can invoke the cheat code, which is you will invoke the idea that I can approximate this as a normal distribution, leveraging the central limit theorem. And if I take P1 and P2, right? So your P1 here is the probability that at first birth is greater than 30 in the case women. P2 is the probability that age at first birth is greater than 30 in control women, right? So this is P1 and this is P2. So it's very important that you figure out what is this interpretation of this number, right? P1 is the probability of that the age at first birth is greater than 30 in the case women. So I have fixed this. I am calculating P1 with respect to that. Okay. Similarly, which is what was given to me also, by the way. And this is among the women who are not developing cancer, what is the probability of them giving birth at greater than 30? The reason I'm doing this is because that's what my question asks, whether this difference that you're seeing between P1 and P2 is that statistically significant. Okay, everyone with me? Tanvi? All good?
Vertical conditioning makes no sense.
That is way more intuitive to me.
Oh, is it? Okay.
Even what is your question? Like, what is your not in terms of mathematics, but in terms of English?
Yeah. So let's focus on the question. Let me highlight that particular part, which is important, right? The hypothesis is that the risk of breast cancer increases as the length of this time interval, which is when you're having your first baby, that increases. That is your hypothesis.
So we separately see a larger time interval in those who gave birth after 30 and those who gave birth before 29, and we compare the risk of breast cancer within those two groups.
So you compare the risk of breast cancer in
The vertical.
in the vertical. So you will try to think about that among the women who gave birth. Here you have already conditioned them on the fact that this is greater than or equal to 30 and that is less than or equal to 29. I will shortly answer your question. The direction in this case does not matter. I will shortly show you why that happens. The reason to fix this P1 and P2 is to show that what we are essentially asking here is, given a particular case scenario where a person has developed cancer, did it happen highly in, is the ratio of the women who have given birth at a higher state, is that proportion larger or not? It will boil down to the same question that you're asking in just a bit, right? So once I unravel it, it will become clear why that happens. Okay. Any other questions? Okay, so here we have defined our P1 and P2 to be a particular, to have a particular interpretation. We're going to flip it in just a bit. Here, if I just now approximate this as a binomial, what is the mean of your normal distribution for a binomial? If X is binomial, what is this equal to? And this? And P? So you know the mean and you know the variance. You can put it to CLT test, right? Centralized limit theorem test. This is what this essentially represents. N1 and N2 are your overall values for this cases. So that sum is N1 and this sum is N2. You're essentially asking if this difference now, which is P1 minus P2, this is a difference of two binomials. We very briefly touched upon this in the last class, right? So this is where we had stopped our discussion, which is, so I'll quickly cover the intuition behind how that formula comes in. So if x1 follows a what is the distribution of, intuitively, of course we can't, we'll not go into the derivation, but intuitively what do you think?
V1 minus normal, V1 minus V2.
And are they independent?
Yes, good question. They are independent. We'll assume that.
So it's
Why? So why did I make that statement? Because that's what we started. Right? So that's why we're not just forcing you to just assume something. In this case, those are independent. Okay.
the sigma was from
Who said it? You said, of course. Okay. The IOR can. Okay. So you owe an explanation to everyone. Why is it plus? Okay. So I don't know the maths, right? Like let's say I cannot do this, but we can still all think intuitively, right? Okay. Good, very good. So what Anand is talking about is this variance-covariance relationship. So in any sense, right, that this, even if this is not being covered in the class, this is the universal relationship between anything, right? And I can of course change my x1 to be minus x2. The only thing that will do is it will change the sign for this term. It will not change the time for this term because the variance of x1 and minus x1 are the same. In this case, the reason it becomes, so there are only two options, right? So this is how it comes from the formula, but let's assume nobody knows this formula. There are only two possibilities when I do this, right? It has to either sum or it has to take a difference. In this case, hopefully you can see why the variance of the difference will be larger. So this is your 1, this is your 2. The 2 varies in this way and the 1 varies in this way. Now when I take a subtraction of this 2 or even an addition of these 2, it's going to, the possibilities of variations is much larger overall. And that's why the variance is a sum and not a negative sign. There are only two possibilities in P2, right? Which is you either sum it or you do a difference. You can do nice things with Gaussian distribution. You unfortunately cannot do very similar things with other distributions. But in this case, that's the intuition that you require. Right? So when I do a minus of this, right, what happens? Nothing happens. It just goes in the delta direction. And now I sum this. So this variation is still going to be very, very large. And that's why that sigma 1 square is. You don't need to know any formula to take a guess. Right? That's the guess portion. Clear? Okay. So here, if I focus on P1 minus P2, I can make it follow a standard downward distribution. For that, all I need to know is I know that each of them is Gaussian, I know their mean, and I know their variance. That's how you get that recipe formula to test whether this relationship holds or not. Make sense? Everyone with me so far? N1, N2 are the total. P and Q are your equal values. P is the equal value version of it. We'll see what that P is in just a bit. But hopefully this part makes sense, right? This is nothing but the difference between the two values, which is mu1 minus mu2 divided by the variance. The variance is PQ, variance or normalized variance. So this is PQ by N1 and PQ by N2. Right? So this is N PQ and sigma squared by N. If you remember when we do the centralized limit theorem, this becomes, the denominator is at the bottom. That's what this represents. Sorry, this represents. Okay, everyone with me so far? Okay, now we have to estimate this P, right? The P is an estimate of overall what is the probability of seeing the successes in some case. The reason that P is constant is because we are assuming that for both these groups there is only one P that we expect to see. Now how do we estimate that P? What is P? P is the probability of for our null hypothesis. All of this is under the null. Under the null, P1 is equal to P2, which is equal to P. But we don't know that what that P is. So to estimate that P, we do a very simple exercise, which is you had N1 observations here, you had N2 observations here. This was your P1, which is the probability of observing something in this age group. This is again P1, and this is P2. If there is no difference in terms of these two groups, on an average, what will be your P? Right? So on an average, this is the number of observations that you see for group 1. This is the number of observations that you see for group 2. Right? So these are your total observation. P1 is equal to P2 in this case. So this overall, the total number of data points that you have is N1 plus N2, right? Hopefully this is clear. Among okay, so this hopefully let me first get the denominator right. So hopefully N1 plus N2 part is clear. How do we get the denominator part? How do we get the numerator part? The total number of observations that we had was N1 plus N2. Among them, P1, which is the probability of seeing something here in this particular block, that is P1. The number of observations here in this particular column are given by simply multiplying that N1 by P1, which is, for example, 21.6%, 21.2%. If I multiply this by 3220, I get this number. Right? So if this was true, if our overall, if I have to estimate overall what is my success probability, it is equal to observing the total number of successes divided by total number of observations, right? Because in this case, I am assuming both of them to be equal, so it doesn't matter where it came from, this or this. Here I got N1 P1 successes, here I got N2 P2 successes, but in my null I'm not differentiating between these two, right? The null hypothesis is that P1 and P2 are, these two groups are homogeneous, there is no difference. So the number of observations that I got is that total, and that is your default P that you expect. Does that idea make sense? Or no? So why are we doing this? The reason we are doing this is because to estimate whether this is a significant departure from your overall observation or not, you need a measure of what is your null, right? So your P1 is equal to P2, but what is that number equal to? That is what your estimate gives you. That estimate will come from overall this number. So x1 is nothing but the number of cases that you saw in this column. So this is x1 and this is x2. Okay? So my P1 was the probability of seeing cases in the case of this particular age category, in this particular cases category. P2 is the probability of seeing this number. Right? P1 and P2 are both in this one column. Right? So they are actually both number of what is the probability of having a first birth in this category 30. So you're fixing this number, but you're observing this. So this is P1 and this is P2, right? Does that make sense?
So basically we are just compressing it to one column, right? Row-wise compression.
Yes. You have compressed this to say that you don't need two numbers, right? Here, all we are working with is that proportion, because at the end of the day, that is the proportion that you want to test. Whether this proportion is different, significantly different. That's why it's called a binomial test for proportions. That proportion comes from the idea that you have only two categories for each of them. You have a case control. There are two categories. This can, by the way, be more. This is we'll generalize it in just a bit. But these two are two in this case. Okay. We can make it even more. We can also expand that, but for now today we'll keep that to two categories. We are testing for that proportion, whether that proportion that you got is that significantly different or not. To estimate the baseline, we said that P1 is equal to P2, and we have a way to assess how significant that is by looking at this value, because this is our z value. If you know the z score, you know the p value. So ideally, I would take p1 is known here, I would put it here, I know p2, I would put it here, I would put n1, n2 I know, but I don't know what is p. This p came from this assumption under the null. That's why the under the null assumption is very, very important. At this point, I don't know what is p, or I don't know what is q. But I can estimate it because I'm going to say that in the null, these two numbers are going to be equal. So they are, which group they come from doesn't matter. So I will just look at the total number of successes, which is n1 p1 and n2 p2, divided by the total number of all observations, and that is my estimate of it. Okay, is that clear? Any questions about this? This is the normal approximation. So any test that we can do, if we can collapse that to normal, there is value to it because we know a lot about z distributions and z test. Okay. Okay. So we can also do it in a slightly different way. If we don't want to use the approximate assumption of normality, we will invoke a different test, right? And that test is called chi-square test, right? So we'll see what is chi-square and how do we sort of so it will answer the rest of the questions that were asked in just a bit. So what is chi-square? Has it been covered? What is chi-square distribution? Okay, I will cover we'll just quickly take the chi-square distribution. But before we do that, there are a few things that I want to just highlight again. That when we did this case versus control thing, these two are independent set of samples. That's very, very important. We have something which is called a row margin, which we calculated, which is just the sum of these two numbers in each row. That's the row margin. And then we have a column margin as well, which is the sum vertical. This is called a 2x2 contingency table. You will see this kind of design in a lot of case control settings, particularly being used in the clinical trial settings. You give somebody a drug, you give somebody a placebo, somebody survives or somebody gives a reaction, somebody does not, right? Or somebody has a good response, somebody has a bad response. So a very common thematic sort of thing that you will see across categories. That's called a 2x2 contingency tables. The question that we are interested in asking is the proportion, these proportions of successes, whatever that success is that similar in cases versus controls? So the design is constant. There is a case, there is a control, there is a measure of success, and there is a measure of not success, right? And we are trying to essentially assign or measure is the proportion that we get for successes in cases, is that significantly different from what in controls? Okay, that's the common design that you will come across in a lot of settings. Okay, so some math, very, very simple math, which is partly we have already done as part of this exercise, is we can always write this as x1 and x2, which we did previously as well. Once we write x1 here, given that this is one set of observations, the row should sum up to n1. So automatically, once you fix one category and define that to be success, you can calculate the other category has n1 minus x1. Similarly, for the other one, you can calculate x2 and you can call this number to be x2 and this is n2 minus x2. Across the rows, or when you calculate the column margins, those are also the total number of successes that you observed in your entire experiment and the total number of failures, n1 plus n2 minus x1 plus x2, that you observed in your entire experiment. The P1 that we defined was this probability, right? This was x1 by n1. P2 was x2 by n2. And you'll see that how that now it generalizes in this. But hopefully this design is clear, right? It's a 2x2 contingency design. We will calculate something called E11, which is the number of cases, expected number of cases with age greater than or equal to 30, which is nothing but n1 times p1 or n1 times p. We'll see what that p is in just a minute. Why is it the expected number? Because if I have an expectation that there is a inherent level of success that your experiment guarantees, and that success is not dependent on whether I am a case or a control. So that value is fixed, which is P. Then my expectation is if I take whether controls or if I take cases, I will observe certain number of observations to have that success, and that is just given by how many number of cases that I took, which is N1, multiplied by the success probability, which is P. So that E11, which is the number of successes that I observe, if my success probability is fixed, because again in my null case, it doesn't matter I came from this class or I came from the other class. Everything is constant. The total number of successes in this box that I expect are N1 times P. That N1 is the total number of cases and P is my inherent measure of success probability. Is that design clear? Not clear. Clear? Everyone clear? Anisha clear? Not clear. Okay. So let's. So I went out in the field and I'm interested in designing a strategy for whether my drug succeeds or not. So I have a drug. I want to make sure that I want to measure that ideally I want my drug to elicit a response, and that response should be different in the sense that I don't want, let's say it's a good response, so the more number that you see for response, that's good. Okay? There are certain drugs where you want the response to not be elicited, but we'll assume that I'm using this drug so that I can elicit a response. I observe some number here, right? Whatever that number is, some x1. I also observe some response in a placebo trial, but the drug was given to a fixed number of patients. That total number was N1. Okay? So this sum is N1 and this sum is N2. What is my null? My null is the simplest assumption that whether or not I treat a drug or placebo, there is a constant response, constant probability of observing a response or a no response. Okay, that constant probability is P. This design here slightly different from what we've been doing. We've been saying that it doesn't matter, which is what we are saying. Like there's no difference between these two. We are saying that there is a baseline stuff that you can observe in this class. That's the only difference that we are calling out in this case. So if there is a P chance of observing a response, okay, there's a P chance of observing a response, what do you expect that if you do this experiment, how many people who have been treated with a drug will show a response? P is a chance or the probability of eliciting a response by null. In your null case, what is your expectation? That if I see this, then nothing is surprising. It's fine. I expect this. N1P, right? Binomial. Number of trials, success probability of each trial. That is your expectation. Number of successes. Similarly, N2 times. Okay? Clear? Because the reason this is fixed is because you took these people out, right? These are independent samples. So this is one entire sample. This is one entire sample. So there's nothing difference again between N1 and N2. You can call it whatever you want. But this is one entire trial. And that's why you're getting N1P. This is one other entire trial. That's why you're getting N2P. Okay? Hopefully that clarifies. But please stop me if that's not clear. Because that's important for understanding the rest of this. Okay, so we will calculate this number N1, E11 and E12. Again, the moment you calculate N1P, this number is N1 minus N1P, nothing surprising. Or it's just simply N1 times 1 minus P, right? That's what the number is. So let's do that calculation. Let's do that calculation of how many numbers would I have expected if I had assumed that there was no difference, or I was assuming that between these two categories there is absolutely no difference. The moment I fix this P, right? The moment I fix this P, these numbers are automatically fixed, right? Once you calculate this, I get this as well. So how did I get 521.6 there? What is the calculation? How did I get 521.6? Let me flash the previous slide again. Observe. Then you decided the null. No difference. Then you calculated the expectation. So let's do that calculation. Total number of observations overall 13,465. How many number of trials did you see which succeeded? In this case, the success is defined if they are in this category, greater than or equal to 30. Because again, that was our focus category. Doesn't matter what this is. How many number of, based on that definition, how many number of women gave birth at the age greater than or equal to 30? 2181. Okay, so 2181. Okay. What do I do next? Okay, out of 13,465, what is this ratio? Correct. This is your T. Successes divided by total number of trials. What is this equal to actually? Can somebody do this calculation? Otherwise, I'll use point. Okay, I trust you. 0.16. Okay, now this is our expectation of seeing something here. If I do some n number of trials, so here I did 3,220 number of experiments. What is the expectation of seeing a success in 3,220 experiments? Into 3,220. P and n1 times P or n times P. What is this equal to? 521.6. Okay. You can calculate the similar number here. Okay, let's see what we get here. Right. So I've not done the other calculation, but this calculation is correct. This calculation will be correct again because this value is constant. Right. So overall, our expectation of seeing this number is 521. That if nothing had happened, if there was no difference between the two groups, and if I did these many experiments, I do expect to see 521 people who have cancer, who have children at the age of above or greater than or equal to 50. Right? This is our expected matrix. All the numbers here are of expectations. Now, how do I measure? This is our expectation. Actually, what I will going to do is I will contrast this with this number here. Observed expectation. how do I measure the element of surprise? In this case, you observe this, and it's okay. You expected for 683, and I had expected 521. You observed 683. You observed 1400 or almost 1500 people to not have who were controls. The number was 1650. How do I assign it a measure of surprise? Again, intuitively. Yeah, difference, right? So you have to somehow calculate the differences between these two numbers. And the differences will not work because differences are always tricky, because they can sometimes be positive and they can sometimes be negative.
We square it as in chi-square.
Okay, we square it.
So, just get the chi-square value first.
Okay, but what is chi-square?
Okay,
Okay. So there's a very special distribution which is called a chi-square distribution. If your Zi is standard normal, then the sum of your Zi square values follows what's called a chi-square distribution with k degrees of freedom. So if I'm summing k independent standard normal distribution, their square, that follows a chi-square distribution with k degrees of freedom. Okay. It's again one of those things which will appear again and again and again and again in different settings. If we want to also measure how different are our observations from expectations, you can try to pin it in this category where you can assume, or we will not do the formal proof, but if we do OI minus EI, which is where OI is the observed and EI is the expected, that square divided by the expected value, this is known to follow a chi-square distribution. How and what is the formal proof we'll unfortunately not do in the class, but happy to discuss it if you want in a later class once we finish this. Okay, that follows a chi-square distribution. This has two properties. Again, look at the mean and the variance. Mean is k and variance is 2k. It's one of those distribution where the mean and the variance follow a relationship. In normal distribution, there is no relationship between the mean and the variance, mu and sigma square. Here it's k and 2k. That k is constant. So the variance is just 2 times the mean. We will use this idea that any distribution of observation minus expectation square divided by the expected value follows a chi-square distribution. And then we'll apply, again, the recipe works. So we'll apply a continuity correction. Whenever we have discussed this in one of the classes, that all of these values are usually going to be numbers, but we are collapsing that to a normal regime, and that requires a continuity correction. So observed minus expected, and this minus 0.5 that you see is the continuity correction. And for that, you need to apply the absolute value before, because you're going to subtract minus 0.5. If this difference is negative, it ends up adding plus 0.5. That's why that absolute number exists. We'll calculate the chi-square distribution. You will be given the values, and again, when you reject, if the probability of observing something as extreme is very, very low, right? That's when you reject your null hypothesis. It's a distribution which will, by definition, have positive values, and that's why the regime of the values that will be given in this case is the one-sided value, right? Because this distribution does not have the symmetricity which we have seen in other cases. It's a positive. There is no other half. There's only this half. Okay. That distinction is clear. In the Z score, it goes from here to here, right? But in this case, it's only the right half because it's a very positive distribution in that sense. Okay, that's how the chi-square distribution works, and that's the application of the same test that we did, right? So we did 2 tests. Just to remind you what we did, we did first a binomial test for testing whether these 2 ratios were different or not. by doing a normal approximation. If we were to able to just do the binomial test, then and calculate the p-value, that p-value and what we get from the chi-square are going to be identical p-values. So it's that we are doing this, we are solving the same problem using two different approaches. That's why this test started with this alter, which means it's a different way to do the same calculation. Rather than doing an explicit binomial calculation, we're going to make use of this chi-square distribution, again because these values are very easily calculated. Okay? Clear? Okay. Okay, if that's clear, let's try to think about a slightly different problem about how will you solve this. You have done some version of this, I think, in one of your midsems, or one of the problem of midsem. It required you to do some Poisson fitting. So I will read out the problem. You're given a problem where you want to the fitting of a probability model based on the Poisson distribution to the random variable is defined by the number of deaths from polio. Sorry. The fitting of this distribution must have been discussed in your class at some point, the number of cases of polio. We want to develop a general procedure for testing the goodness of fit, right? How good is your statistical model in capturing your observations? How will you, well, it's a very general question, how will you solve it? I will tell you what the problem is. So, you must have seen that the number of polio cases, or you can assume that the number of polio cases can be modeled using a Poisson model. You can fit a model. You can estimate the MLE parameters, you can get the lambda values and so on. How will you measure how good statistically that fit is based on whatever we have discussed in today's class? And this problem is particularly chosen to tell you that whatever we did in the last few slides is generally applicable. It's not designed for one use case. The idea is generally applicable. Okay, what will be the expected and what will be the observed? We can fit a chi-square that way, but what will be the expected and what will be the observed?
So in the test set, if we allow the model to predict, so that becomes the expected and we have the ground truth, and then we can calculate.
Okay. So let me show a quick example. Okay, so Poisson, so usually small numbers. One frequency is 5, 2 is some 4, and something of this sort. This is your observed value. When you do the Poisson fit, you try to fit a curve, essentially, even though this is discrete, but so this should not be taken at the face value. But maybe what your Poisson will try to do is, let's say, it will give you that the lambda is maybe 2.5. The mean parameter of that distribution, Poisson distribution, is 2.5. Okay. Now what do I do after this? How do I measure? I have been able to fit, right? I got the lambda value. You can get this with any statistical software. This procedure is called maximum likelihood estimation. If there is time once we start covering the regression, this has not been covered. MLE has not been. So there is time in the regression setting. I'll talk about what is this, how is this distribution fit us. Yes, right? Yeah, it's a simple one. It's not. This is a very intuitive actually. Okay, so any statistical software, right? Like it will give you that. Okay, fine. This 2.5 is the value. How will you measure whether this is correct or not? Or how will you measure how good is it in capturing value?
So we synthetically generate from the model we have, right?
Okay.
So the value at 1, 2, like in the x-axis, considering the values of x, we get the y cap.
What is the distribution?
whatever lambda.
I always get it wrong. But where is x? There is some. What is Poisson distribution?
Lambda to the power x.
Everything else is correct?
Yeah.
Okay. Yeah. So this is your probability distribution function, right? Now here, so very good. So you can calculate for each, given your lambda, you can calculate what is this is frequency, right? This is frequency which you can normalize to 0 to 1. You can calculate the probability after fitting the lambda values, right? So this is, I said 5, but that's 5 by, so this is 5, 4, 3 and maybe 4, 5, 4, 9, 3, 12, 16. So this is 5 by 16, 4 by 16, 3 by 16 and 4 by 16, right? Let's assume that this is the sample space for that. If I plug in that lambda equal to 2.5, I can, for each of these observations, so I can put my lambda, my x is 1 for this case. I will get e raised to minus lambda. That's it. This is the probability density of observing x equal to 1. Similarly, I can do the same thing for, oh sorry, I forgot the lambda. This is lambda square. Factorial. This is for 2. Let's call this, what should I call it? So I'll call it E1. Having given a lambda, this is the expectation that you have for observing whatever a distribution which follows a Poisson distribution. This is on the other way O1. And like in any setting, if I want to test whether that lambda equal to 2.5 is a good fit, will be to measure this value. And that's broadly what's called goodness of fit test. Okay? GOF test. So we'll do some of this once we start talking about regression, but the concepts are fluid in that sense, right? Like the same methodology that we developed for one use case actually applies in doing a general goodness of fit test. Okay? Can do the same goodness of fit test for regression problems as well. We'll cover this once we start talking about regression. Okay, so any problem, right? Like goodness of fit test. That's what this is usually used for. Even if it is, this is taken from my other class example. This shows the distribution of birth months. I wish I could do the same exercise here because it's a very interesting exercise to do. Any observations about this plot? Tangential, totally tangential exercise. There is a in Jan, October. Yeah. Why?
Month of conception.
Okay. Month of conception. Okay. So what happened? Jan conception happened in what? March.
So people are more likely to conceive in certain months.
Okay. And why?
Weather conditions, rituals.
You are not allowed to answer. Okay. Okay. Anyway, that's a separate topic. Hopefully, we'll see some flavor of it later on. It's a biostatistics class, so we'll keep to statistics part. There is a different way to think about this, and maybe you have done at some point. You would have come across this distribution. But very simply, we'll talk about what that thing is in just a bit. But if you want to do this in R, it's very simple. You have a contingency table. You create that contingency table, and you just run chi-square.test, and it tells you whether these differences are significant or not. Okay. Okay. Yeah, I will skip this actually. We have time. Okay. So let's talk about this example. We're going to come to a different distribution, but let's talk about this example. While you're reading, I will clear this up. Okay, what do we do first? Design. What should I write this as? Okay. Case control. Sorry. Yeah. Okay. So, case. What is case here? CVD, right? That's the case. High salt. And what are the values? 35 people died from CVD. 5. And what is the bottom one? 25. Okay, how do we assess whether more people die or do people die more because of high salt in their diets? How do we test this? Oh, why people are dying because of high salt? Actually, that's a very good question. You have doctors in the audience who are better suited to answer this question, but I will give my take. So, I think there are few bold predictions. I think the next 10-20 years, people in India are going to die because of number one reason why people will die in India. Huh? Before that, there is one more.
Diabetes.
Yeah. And usually, the combination will also have all the things that go wrong. Right? So hypertension leads to a lot of course, tension is not good in any sense, and that affects different parts of your body, including the heart. It's all circle. Actually, it is all indeed a circle, right? Like I could have started from obesity and correlated all of them together as well. It's all a circle. It's all connected. Okay, so hopefully that answers that question. Now,
Yes, so salt, higher salt intakes actually worsens hypertension.
correct. So if you have hypertension, you are advised to go on lesser salt or avoid iodized salt and so on. Okay, that's a separate discussion. That's biology, but this is statistics. So from here, what do I solve? How do I solve this? Okay, expected. I can find the expected. So that we'll find the P, right? This is 35. This is 25. P is 7 by 50. What? 60. P is how much? 1 by 9. 1 by 9 is 0.1. Right? 1 1 1 1 3. Okay, N35, anything that stands out? We had discussed this before we started talking about the, and you will do this as an exercise, and we start talking about the approximation. There are values at which the approximation fails, the normal approximation fails. Yeah, n less than 30, n less than 20, broadly those assumptions start to fail, right? And whenever those assumptions start to fail, then any approximation that you do either with the normal or even the chi-square assumption, those are not fully correct. Again, you can go ahead and do it, but those will not be fully correct. How, in those cases, how do we solve this? These are small numbers. How would you run student T?
It's the same statistic.
Same?
Statistic.
But in this case, how would you run a student T? Because again, you don't have access, right? So students T, right? Any of those tests that we talked about, you require individual level observations. Here, it's still a summary, unfortunately, right? You don't have, it's a binary cause. It's not like a quantitative or an ordinal or a nominal variable. Figured out? No? So this happens a lot in genetics. It happens in when you do. Have you studied Mendel's experiments, P crossing, and so on? There are some numbers, but of course this was Mendel and genetics. Those times used to be very small sample sizes, right? Like very very small numbers. So somebody devised a way to do these kind of small sample testing. And that's called the Fisher's exact test. So again, the idea is very very similar, that you want to test whether these set of observations are statistically different. You start from this assumption that they follow a particular kind of distribution. This distribution is called a hypergeometric distribution. This is a total number of marbles that you have in a box. People have seen hypergeometric. Nobody? Okay. So very simple way to remember is you have a box. Okay, there are black and white marbles here. There are total of n marbles. Now, when you pick out a few of them. So let's say you pick out k marbles at random. So I'm not seeing, but I put my hand and I pick out k marbles. The distribution of number of black marbles here is a hypergeometric random variable. I took out k, and out of them b are black. That b follows a hypergeometric distribution. Just like Poisson, just like negative binomial or any other count variable, this is called a hypergeometric distribution. Again, it is being invoked because there is one choice. First choice is whether you pick or you don't pick. Right? If you don't pick, then of course you're on the other side. And if you got picked, then what is the chance that you are black or white? So categorization. One level of categorization. So total chances, one level of categorization, and second level of categorization. Okay? That's why a hypergeometric distribution.
Is this same as the geometric distribution?
No, it's not. In geometric distribution, you are looking for the number of failures before you get a success. Right? So how many number of times same experiment, very good question. Same experiment, now I'm seeing, I'm going to pick randomly the number of black balls that I pick before I pick a white is a geometric distribution. But the number of black that I see in a given random trial, that is distributed hypergeometry. So there's a subtle difference there. Here I'm keeping track of, I will stop my experiment if I see one white ball, and that is how many number of times I tried before I saw. So if I tried black, one try, and then I see a white, I stop my experiment here. I see black, and then white. So this is try 1, try 2, and so on. This is distributed geometrically. But when I take a few of them, that K is fixed, right? And among them, how many are black? That is hypergeometry. So there's a subtle difference in geometric and hypergeometry. Here,
If K is small, it will be geometric.
if K is small, if your chances of success is small, that's a good question. Probably, but I don't know at the top of my head. But good question for simulation and trying to figure out if it matches up with the geometry. Yeah, there was a question.
Where is the parameter K in the distribution?
The K here is, there are two ways to think about it, right? One is, again, there is some exchangeability here. So among these n people, how many of them started having a high salt? That is, you're deciding to be K.
Pick versus not pick, black versus
Exactly. Pick versus, so this is your pick, and then which of them are black here in this case. That is a hypergeometric distribution. In R, again, never ever will you do this calculation by hand. It makes absolutely no sense, and I will never ask you that question. You can do this as part of your assignment, and in future, very simple command, fisher.test table. The only assumption, so again, this is one thing which is generally applicable, right? There are no magic numbers here. This test is always possible to do. You will do this only when small sample cases, because otherwise this command will take longer. That's it. But otherwise, that test is always true, right? Again, probabilistically, what is happening? We are looking for, this is what I had originally started my lecture with, saying that why is that number, whatever you're observing, what is so special about that number, right? What is so special about that number? Because if I fix this size n1 and if I fix this n2, then there are so many combinations that can happen. But hypergeometric essentially tries to capture that. So it is, the way we are quantifying this is we are quantifying that probabilistically, that among the so many possible permutation combinations of these numbers that could have happened, what you observe, what is so special about it? What is the probability of observing something as extreme as that? That's what Fisher test tries to do. Okay, when we come back, we will tackle a different problem. In all these cases, the cases and controls are independent. We will see that what happens if the independence assumption breaks. And then once, this will be just a couple of slides, and then once we come back, we'll start regression. Maybe I'll spend more time on regression than usual, than I had planned, because there is some demand about being able to understand it at depth. So we'll spend some more time doing regression before we go and switch back and try to do other survival models relevant to biostatistics. Okay, thank you.